So first, let's go ahead and read our problem and figure out what our given and goal are, right? So we have 1.33 grams of sodium iodide, right, which is a mass, and it's added to some amount of water, and I would like to know the concentration of my solution, right? So the concentration is my question. Concentration is moles per liter. So all I'm doing is I'm taking something and adding it to water, specifically sodium iodide, right? So here is where we need to know our reactions really well, because we'd be like, oh, sodium iodide plus water, ionic compound plus water. Does that? No, that's not a chemical reaction. So we're going to take our 1.33 grams of sodium iodide, and then we're going to use our molar mass of sodium iodide. And then we are going to divide by my volume of my solution, and that is going to give us the correct answer. Rounded to 3 sig figs is going to give us this. And that would be our final answer. Yes? All right. Next up. This one says that I have 20 mils of 2.0 millimolar solutions, plural, of phosphoric acid and strontium hydroxide, and they are mixed. So, what do I know I have to do before I do anything else? Right, let's start with the reaction. So I have phosphoric acid, and since I have a concentration of each of these, I know it's aqueous, right? Strontium hydroxide, also aqueous. I don't know why I didn't start it further over, which is then going to give us a double displacement neutralization. Solid, courtesy of solubility rules, H2O, and then we would go ahead and balance. Okay, now, and then I know the amounts of each, right? So I know that I have 20 mils of 2 millimolar, and I have 20 mils of 2 millimolar, right? Which means that that's a huge clue that you also need to, right, come up with a limiting reactant. If we continue reading the problem, it asks us, what is the percent yield of this reaction if 6 milligrams of strontium phosphate are collected? So that means specifically the problem gives us direction that we want to talk about strontium phosphate, so we're going to make that our goal, right? So we want to figure out grams of this, or in other words, that would be our theoretical yield of that, right?
Sign sodium for salty times magnesium, aluminium, silicon, phosphorus, and sulfur, chlorine, and argon, potassium, and calcium, so you'll grow strong, scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table. No gas is stable. Halogens and alkali react aggressively. Each period will see new outer shell. Electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel, points again, copper, zinc, gallium, germanium.
So then to get to the actual end part, right, so again, what this says, right, thinking about all the things that we know, right, if I start from 20 mils of H3PO4, I could make this. If I start from 20 mils of strontium phosphate, I could make that. But once I make this 0.006 grams, I will have run out of strontium hydroxide, which means that's the most I could make, which means I will have excess of my H3PO4 running around in the solution, so there will be left over that. But this then becomes my theoretical yield, which means that that's what I'm going to employ over here. So I will take my 6 milligrams of actual over my 6.04 grams of theoretical, and do that, and that's going to give us as our final answer. Yes? All right, next up. This one says, what volume, question, right, of 12 molar hydrochloric acid is needed to make 5 liters of 1 molar hydrochloric acid? And then subsequently, what volume of water is needed, right? So I'm talking about a 12 molar HCl from which I would like to make 1 molar HCl. So this is dilution, right? I have one thing and all I'm doing is making it more dilute, right? which means that I could employ M1V1 equals M2V2, or I could just do it with basic stoichiometry like we've been doing for forever now, right? So 5 liters of my HCl and 1 mole per liter, right, of HCl. This piece of math right here solves for how many moles of HCl I need, okay? And then this is where my moles are going to come from. So if I break this up into its parts, right, this is my dilution. That's how many moles I need. And this is my stock from which I will get those moles, right? So if I do that math correctly, I come up with 0.42 liters. And then this is the volume of my stock, or 12 molar HCl, that I need, yes? All right, so then the second question says what volume of water is needed. So if I need 0.42 liters, my total stock volume is going to be 5 liters. That difference is what's going to give us the hypothetical amount of water, assuming that the volumes are additive, yeah? All right, so this is answer number 1, this is answer number 2. Okay, so next question asks us, what volume of 2 molar HCl is needed to neutralize this much calcium hydroxide? So note that you might be tempted to be like, oh, well, look, we got some volumes and some concentrations again. Oh, these are the same problems. No, absolutely not, because here we're talking about HCl. Here we're talking about calcium hydroxide, which means, right, balanced chemical reaction, HCl aqueous plus CaOH2 aqueous gives us CaCl2 aqueous plus liquid water, right? 2. So I would like to know the volume of HCl, and it's 2 molar, needed to neutralize 0.25 liters of 1 molar this, right? We are going to start with our 0.25 liters, and again, these molarities, right? If that is confusing, stop and rewrite them, right? So 1 mole of CaOH2 is equal to 1 liter of CaOH2, right? And when you do that, that tells you, oh, this is a conversion factor, not a given. This is not how much I have. This is a relationship between how many particles, because moles are basically particles, right? How many particles there are per unit of volume. So we're going to start with our 0.25 liters of calcium hydroxide. And then we are going to use our molarity. So 1 mole of calcium hydroxide for every 1 liter of calcium hydroxide. And then for every 1 mole of calcium hydroxide, I require 2 moles of HCl. And I know that there are 2 moles of HCl, again, a relationship for every 1 liter of HCl. And so now we can do that math, right? Where if we take a look, right, actually those 2's cancel, and all we have is 0.25 liters of our HCl solution. Make sense? Okay. And if we stop and think about it, right, that number makes sense, right? Because this equation says that I need twice as many moles of HCl as I need of calcium hydroxide, right? And the concentration of my HCl is double. Therefore, right, it makes sense that I would need the same volume. Yes? All right. Next up, what volume of 0.75 molar iron 3 chloride contains 2.5 times 10 to the third ions of Fe, right? So here is ions of Fe. When we see this word ions, what should we be thinking? Right. Ding, 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 Avogadro's number somewhere. And here I am talking about iron 3 chloride, and my question is a volume. So, 1, I'm going to have to employ Avogadro's number. In addition, if I'm talking about iron from iron 3 chloride, what else am I going to be using? Right, piece versus whole somewhere. So, piece versus whole. So 2.5 times 10 to the 30th ions of Fe. Okay, so as is often the case, right, there are multiple places that we can tie this back in. I am going to go ahead and tie this back into ions of Fe per every 1 mole of Fe. And then for every 1 mole of Fe, I know that there is 1 mole of FeCO3, yes? As in that's a relationship that I know. And that for every 0.75 moles of FeCO3, it requires 1 liter of FeCO3. Right. Alternatively,
Assign sodium for salty times magnesium, aluminium, silicon, phosphorus, then sulfur, chlorine, then argon, potassium, and calcium, so you'll grow.
So whether I decide to do piece versus whole at the particle level or at the mole level, right, doesn't really matter. Just as long as I relate the piece versus the whole somewhere, I am going to get the job done, right? If I wanted to add in a couple extra steps, I could even do piece versus whole at the mass level, right? And that would be okay too if that's what makes more sense to you. And if you want to come chat about how to do that, we can. But as it stands, using either of these methods, we would get this ginormous number because I did not choose my numbers wisely, and 5 times 10 to the 30th is a ginormous number of moles. If we think about 10 to the 23rd is 1 mole, 10 to the 30th is like 10 to the 7th-ish moles, and so I just did not set up the problem very well, which is why we get what is a ridiculous number of liters. All right. Which should make sense because I picked a ridiculous number of ions, right? So moving along to the next problem. The next problem says that we have 25 mils of aqueous phosphoric acid, which react with 14.35 mils of that, and I would like to know the concentration of my acid, right? So this is kind of like the EOC number 93 and the Skill Builder Plus from the book. Where it's important to note, right, that one, we do have 2 different chemicals, right, which means that we are going to have to do a chemical reaction. And let's do that first. So we have H3PO4 aqueous plus NaOH aqueous, and that's going to give us our sodium phosphate aqueous and some water. Okay, then we do need to balance. All right, so if we were to summarize our information, we know that we have 25 mils of this, 14.35 mils of this, and 1.0 moles of NaOH equal to 1 liter of NaOH, okay? So, again, you might look at it and be like, ooh, I don't know if I should start with the 25 mils or if I should start with the 14.35 mils. But here, if we summarize this, right, it should be crystal clear that we have to start here, right? If I only know milliliters of H3PO4, that is insufficient to go anywhere, right? We can't do anything with that. But I do want to know the concentration of it, which means that I can get to moles of it and then use the volume to figure out the rest of it, okay? So even if you weren't sure what else to do, this is where we have to start, right? And then we have to get to here, right? So let's go ahead and 0.01435 liters of NaOH, 1 mole per liter of NaOH. And then for every 3 moles of NaOH, I would require 1 mole of H3PO4. And then I know that there are, oh, no, not there. And so now I'm at moles of H3PO4, so I can just go ahead and divide by my number of liters. It's 0.25, right? Yeah. And that should give us 0.19 molar H3PO4. Good? All right. Thanks for listening. Be good. Study, 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 and I will see you soon. Bye.